there was a couple points. Let's look at problem set number 2. If we go to the book and look at number 2.1G. This problem had asked you to come up with a cell diagram for the overall reaction, 3 triiodide molecules plus 2 irons going to 2 iron 3+ species and 9 iodide ions. And the question was, can we draw a cell diagram? And if we draw a cell diagram, is that overall reaction is written, is that a electrolytic or galvanic, a spontaneous or non-spontaneous process? Basically, it's simple enough. We see that the triiodide is being reduced, and so we can write a cathode half reaction that is involved in that. We can look that up in the back of the book, and we see that there's a reaction for I3 plus 2 electrons going to 3 iodine molecules, and that's 0.5338 volts. At the anode, the reaction would have to be 2 iron 3+ plus 6 electrons going to 2 irons. Actually, we could have just 1, 3, 2, 1. But if you look in the back of the book, you see there's actually no listed value for that. Now, you can do what Imad did and look up in the library and find one. Or you can actually solve this, because what we have is we can combine half reactions to do that. And I want to just outline that briefly, because that's something where we do have to be a little bit careful when we're combining half reactions. For example, if we combine a half reaction for the iron 3+ plus E to go to iron 2+, we actually know that there's an E0 for that. There's also an E0 for iron 2+ plus 2 electrons going to iron metal, and also an E0 for that in the book. Okay, and then the overall reaction is the one we want. Unlike the previous situation where we could just simply add up the E0s, in this case we cannot do that. And the reason for that is that, unlike a normal cell reaction where there's no electrons left over, in this reaction you see that there is still electrons involved in the situation, in the process. So what we have to do is go away from our shortcut method of simply adding the cell potentials and go back to adding the free energies of the reactors, which is really what's being added up. So in order to do this, we have to let's take this as being delta G of, remember, delta G0 is equal to minus NFE0. And so if we add delta G0 for species 1 and delta G0 for species, or for reaction 2, now we get a delta G that's the proper delta G. And from that we can extract the proper E0 for the system. Now the Faradays do not change, so we can immediately remove those effects. But in order to add the delta G's, we can multiply the number of electrons times E0. For the first reaction, 0.770 times 1 is equal to N E0. And the second one would be minus 0.409 times 2 is equal to N E0. And we get a result that's minus minus 0.048 times N, which is 3, equals to N E0. And so E0 in this case, for the reaction 3, is minus 0.016. And so in this case, where we're adding the half cell reactions together to get a new reaction, we do have to take into account the number of electrons involved in the system, because we have to consider it as being a sum of free energies. We don't normally have to worry about that when we're adding the free energies for this, because we always make it so that the number of electrons are the same for the cathode reaction and the anode reaction. And so it cancels out all the time. But that's the only reason we don't have to do it that way. And so we would just put in our number here, minus 0.016. And then the E cell. There's a lot of different ways. The one way I remember is, I always have trouble sometimes remembering it, but if you subtract the reduction potentials from the cathode to the anode, you'll get the proper result. Uh, 0.550 volts. And the cell, you have the iron 3+, aqueous. We have to have a salt bridge or a porous separator. And that would be our cell. And that would be a spontaneous reaction, plus 0.55 volts, so it would be a galvanic cell. Now, if you look it up, you'll see a different number, perhaps. But it depends a little bit on what you get. But this would be the calculated one. Experimentally, you might actually be different. People might have measured it and found a different number. Okay. And notice again, the way we've done this is we've not inverted the EMF for that system. We're taking the reduction potentials as they're written in the back of the book, or as we've derived it here. So E0 is equal to minus 0.016. So we're not adding EMFs, we're actually adding E0s for the system, or subtracting the E0 from the anode. Okay. I think 2.4b, we can quickly go over that. That's an example of a problem that is a Nernst equation problem that relies on substituting in the proper, the different concentrations. And so they give a cell reaction like so. Okay, so you have iron 3+, iron 2+, copper 2+, and HCl in the system. They're asking what's the overall cell potential. They're not asking in the question what's the E0 for the reaction. They're actually asking what the cell potential is as it's written. So you can distinguish that from a standard cell potential, which would be the E0s of the system, and the actual cell potential. Well, the anode, as always, is equal to, or the anode is always the one on the left, and typically that's the convention. That E0 prime is a formal potential because it relies on the fact that it's in 1 molar HCl. And that's what we see. The cathode is copper 2+ plus 2 electrons going to copper. The formal potential for that particular is 0.34 volts. So here's the standard cell potential. E0 cells, as always, the cathode minus the anode, and that would be equal to minus 0.43 volts. But that's not what we're asking. The cell potential is the Nernst equation. And we have to look at the overall reaction to get the proper form of the Nernst equation. In other words, according to the reaction that we've written, we're having two iron 2+ ions plus a copper 2+ ion going to two iron 3+ ions in copper metal. And so in the Nernst equation, the way we've written it with a negative sign there, what's going to be on the top is the right-hand side of the equation. So that would be iron 3+ squared over iron 2+ squared and copper 2+. So this should not be anything new to you guys, but maybe you need a little bit of review. Again, we leave the copper out because it's a solid material activity, and the concentration is not included in these sorts of calculations. And you'll find that then the E cell is equal to minus 0.4 volts. So that's a non-spontaneous reaction, as you might anticipate knowing anything about copper and iron. .5 is, I'm just going to quickly outline the steps. I'm not going to do the whole thing, but basically it's asking you, taking the cell in 2.4F, which is iron and cerium-4 mixed together, what will be the concentration of the species present in that cell when equilibrium is achieved? So the critical aspect of this question is equilibrium is present. So first of all, a little bit further down this question, it says, what's the potential of that cell? Well, the potential of a cell at equilibrium is going to be 0. So the cell potential is 0. That does not necessarily mean, though, that the half reaction potentials are 0. Cell potential is 0. What else do we know about equilibrium systems? Well, we know that at equilibrium systems can be characterized by an equilibrium constant. And by knowing the relationship between the equilibrium constant and the standard cell potential, we can actually arrive at the equilibrium constant for our particular system. Now, depending on whether we write this as an electrolytic or a galvanic cell, we'll get a different equilibrium constant. It doesn't really matter. You can do it either way. But I left it as an electrolytic cell, a non-spontaneous cell. And in that case, the reaction equilibrium constant would be equal to the exponential 38.92 reciprocal volts times the E0, which is minus 0.67 volts. And so 4.73 times 10 to the minus 12 is the equilibrium constant. And so just like any equilibrium system now, we can actually use this to figure out from an initial concentration what the final concentrations is at equilibrium. And we do this in freshman chemistry all the time. So let's remember, all we'd have to do is set up an equations like this, where we put in the concentrations and we see that the iron and cerium concentrations will change by some value x, and they will decrease on one side of the arrow and increase on the other side of the arrow. And x can either be positive or negative at the end. You just solve for x, and we find that x is approximately equal to 0.01. That means, according to our system, that we've got approximately 0 moles of iron 2+ at the end. which is that's the sort of limiting reagent in our situation. So all of the iron 2+ is basically gone, although it is not exactly gone. It's some 0 plus a very small value. And you can actually find out what that is by substituting back into our equilibrium constant. And I'm not doing all the steps, but you should be able to follow along if you've done the problem, or you should do it, and then you can follow along. And you see that would be true, and then we see that the concentration of iron is approximately 10 to the minus 13 molar. It's actually 1.05 times 10 to the minus 13. So not 0, close to it. And if you put those into the half cell and use the Nernst equation, you can actually get the right half cell potentials. So that's not too hard, I don't think. But it did require you to think back to freshman chemistry to solve it, which is often the case. Okay, 2.5 can be done a couple different, or 2.8 can be done a couple different ways. You guys did it the hard way that did it right. And so let me just show you the way I did it, which is a little bit simpler conceptually, I think. The question is that if I have a cell, and for example, it says copper, and then it has a metal, and then, I forget exactly how it is, but there's a inert metal at the solution interface. And so the metal can be whatever, as long as it's inert. Does it make any difference what the metal is? In other words, suppose we want to use gold or platinum as the metal. Will it depend on anything in the system? Again, assuming both gold and platinum are perfectly inert, there's no effect of the surface. The gold doesn't catalyze anything, platinum doesn't catalyze anything or anything like that. Suppose there is two metals, metal 1 and metal 2. What we can do is consider then that the solution and metal 1 potentials, let's try that again. Can be subtracted from the potential from the solution and metal 2. And those would be equal to the chemical potential of the electrons in those metals divided by the Faraday. So at the solution metal interface. And so that would be, if there was a difference, which there would be, actually, that's the difference that we would see. However, if we then look at the copper metal interface, so we've got, again, remember we've got copper, metal, solution. So we've looked at this interface. Let's look at this interface. We would find that interface would be phi M1 minus phi copper. That would be the difference at the 1 minus phi M2 minus phi copper. And we would find that in that particular case that the chemical potentials in the metal 1 minus chemical potentials in the copper, of metal 2 I should say, over the Faraday. So what you see here is that those two potential differences are equal to each other, and they would cancel each other out. So that any difference in potential that arises at the copper metal interface is canceled out by any difference in potential that arises at the metal solution interface. So that suggests that there is no difference depending on it. And you can solve it a different way, like the book kind of outlines a different way, and it gives you the same basic result. All right, well, let's stop here. Let's take a break. And I've also, what I've done for you guys in the that want to take a look at it, I've scanned in the notes, solution set for the problems, and I put it on. I'm going to put them on the web page. They're not on there right at this particular moment, but this evening they will be on there, so you can go to the web page and download the solution sets for the problems that are mine. Don't take my solutions as gold. I can make mistakes, but you can use them to check your results and see what you got. Especially the people that are not doing the problems and handing them in. You can check them yourself. All right, let's take a little break.